Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Today I would like to present about FEA analysis on bike frame. Okay, so let's go. So as you can see, this is our group member, which is first one is Muhammad Aiman bin Anis, second one is Muhammad Alif Afifi bin Muhammad Baharudin, third is me, which is Muhammad Aiman Hafiz bin Marusdi, and the fourth one, which is Muhammad Aidil Haziq bin Syari. So moving to the background. So as you see, FEA is commonly used to enhance bicycle frame performance by analyzing stress and deformation. So different varieties of bicycle having varying loading circumstances necessitating accurate modeling for safe and effective design. So moving to the problem statement. So as you know, mountain bikes are subjected to a great deal of stress from rocky roads and jumps. If the frame is not robust enough, it may crack or become damaged. So it's difficult to tell where the weak places are merely to looking. So it require FEA, which is finite element analysis, to test the frame stress and ensure its safety and reliability. So moving to the objective, we have three objectives that we want to achieve in this analysis. First one is to design a main frame of a mountain bicycle using CAD software. So the second one, to conduct a finite element analysis, which is FEA, on a bicycle model and analyzing bicycle frame based on the individual state. And the third one is to examine the total deformation and max stress of the bicycle model.
So thank you, Aiman Hafiz, for the introductions. So my name is Muhammad Aidil Haziq. So I'm going to talk about literature review, the methodology, the flowchart, and also the 3D modeling. So basically, the literature review, as a mountain bike are subjected to a complex and repetitive load. Finite element analysis (FEA) is increasingly becoming a key tool for our evaluation structure performance to assess the fatigue behavior under repeated loading conditions. And it's conducted a detailed FEA study on aluminum mountain bike frames. In the analysis, the down tube and the bottom bracket junctions were more stress critical area, highlighting the most important of accessing long-term stress accumulations rather than considering only peak impact forces. For the next one is in a 2022 study, Raimi and Lim explore how the change in the tube size of wall thickness affected a bike frame strength during the impact. They discover even the slightest reduction in the thickness can noticeable and lowering the frame ability to withstand the vertical drop. This highlights the value of using FEA to test the various frame design and find the right balance between the durability and also the weight. Chen and Wang in 2019 study how the rider body positions such as standing while climbing or sprinting affects the pressure applied on the bike frame. They found that this riding position increased the stress in the specific area, especially in the near of the front of the frame where the top tube and the head tube connect. The research showed the importance of a test bike frame under the various real-life riding conditions, not just while seated. As for the methodology, the process started by creating a detailed 3D modeling of bike frame using a SolidWorks and to match the real-world dimensions. And this model was then brought to the NCs for testing, which is the FEA. There, the frame was broken to the tiny pieces that we call mesh to make the simulations more accurately. Important material details like how the stiff or flexible the frame were added, and realistic conditions such as where the frame is held in place and how much the weight is carried were applied. The software then checked how the frame bends or stretch under the pressure and how much the stress is experienced. It's also calculated the safety factor to see if the design is strong enough. This helps spot any weak area and we can improve the design for the both safety and also the performance. So for the methodology, as you can see here, we do it from the start, and then we go to the literature review. After that, we go to the finalized selections of the material and design. create the bike frame, which is our bike, which is the mountain bike, on ANSYS and SolidWorks. Optimize the parameter, update model and FEA, sign load, mesh in the model, which is we're using the ANSYS. Analysis the bike frame, which is the mountain bike, and if it's bad, we're gonna go to the literature review back, and if it's good, we're gonna go to the state the result, and after that completion, and after that to the end. So this is our 3D model of mountain bike, which is as you can see here, there's a top view, side view, isometric, and also the front view. And the mesh data we use, that we have 37,186 nodes, 16,675 elements, and average the surface area is 0.0027 2714. And you can see the density is 7,850 kg. The thermal of expansion is 1.2. Specific heat is 434 joules. Thermal conductivity is 60.5 watt. And the resistivity is 1.7. So basically, that's all from me. Thank you.
So thank you, Haziq, for your presentation. I will let you take it from here. So hello everyone, my name is Muhammad Mabi Anis, and today I would like to present to you guys about the boundary condition for each state for our simulation. So this is the first state for our simulation, which is the seated pedaling. As you can see here, we place two types of force on the front and on the middle. So the first one is on the force on the head tube, we put it around 1,500 Newton, and over the force 2, we put it in the seat tube, which is 3,000 Newton, and lastly on the drop up, we put the feet support on it. So next we move on to the boundary condition for the stand pedaling. As you can see here, the force is still the same. We put two types of force and one feet support. So the first force is force A, still in the same, which is the head tube. We put it 1,500 Newton. And next, the second force, which is on the bottom bracket, we put it around 3,000 Newton, because on the first step we actually put it on the seat tube, but now since there is this the stand pedaling state, so we move it to the bottom bracket, because the cyclist will not sit on this kind of state. And lastly, the same placement for fixed support, we put it on the dropout. So lastly, we move on to the boundary condition of the drop-off impact. So this analysis simulates the real-world impact scenario where the structure experiences a sudden drop from a certain height, so commonly known as a drop test. So as you can see here, we selected 3 points of force and also still the same placement for the fixed support. So we move on to the first force is on the head tube, force of 1,500 Newton, and the force C on the bottom one, which is the bottom bracket, we put it around 3,000 Newton, and lastly on the seat tube, we also put it 3,000 Newton to simulate the drop test for the simulation. So next we move on to the preliminary result for each state simulation. So as you can see here, this is the result for simulation of total deformation. So as you can see, the first state, which is the first picture, is the seated pedaling. We got the maximum deformation of 0.19047 meters. So next, for the stand pedaling, the total deformation is 0.22207 meters. And lastly, for the drop of impact or drop test simulation, we got it around 0.3 meters. So next, this is the total stress for our simulation result. As you can see, the first one will be referred as the seated pedaling, the second picture is stand pedaling, and the third one is the drop-off impact. So this is the result for each state. We go for the first one, which is the maximum stress that occurred during the simulation is For the city pedaling is 1.4 times 10 the power of 10 Pascal. Next is stand pedaling with a 1.5 times 10 the power of 10 Pascal. And lastly, the drop of impact with the total of 2.225 times 10 the power of 10 Pascal. So I think that's all from me. We move on to the next slide.
Okay, thank you, Aiman, for your presentation. So today, I would like to continue my part. So my name is Muhammad Alififi bin Muhammad Baharudin. So this is the preliminary result from the 3 different scenario. For the first one is the seat pedaling, and the second one is stand pedaling, and the last one is the drop of impact. So we can see here for the maximum value of the safety factor, they actually the same value they have. This is 15 for the maximum. We can see for the first picture they have a 15 maximum value, and the second picture for stand pedaling they have the 15 also the maximum value, and the last one also same value at the 15. So the next one is minimum safety factor value. So they have a different value. For the first one, for seat pedaling, they have a 0.017753, and the second one is stand pedaling have a 0.015658, and the last one for the drop of impact is 0.011249. And we can see here why the value is the same at the 50 for the different scenario at the maximum safety of factor. So this is why, because the safety factor result of 15 show that the mountain bike frame is much stronger than needed to support a person weighing around 305.8 kg or applying 3000 Newton of force. This means the frame can handle up to 45,000 Newton, way more than what one rider would ever put on it, even during rough ride or big jumps. In simple terms, the test result prove that the frame is very safe and strong enough to handle real-world mountain biking without any risk of breaking or falling. So the conclusion here, this project have the set out to design a mountain bike frame using the computer-aided design CAD or SolidWorks software, and then test its strength and how much it deformed under different riding conditions using a method called finite element analysis (FEA), which is we are using the ANSYS. So the researchers successfully created the bike frame model and analyzed it for maximum stress and total deformation in 3 scenarios, which is include seat pedaling, stand pedaling, and the during drop of impact, which is 2.225 multiplied 10 PA, followed by standing pedaling 1.59 66 multiplied 10 PA, and the seat pedaling 1.4082 multiplied 10 PA. Similarly, the maximum deformation was greatest during drop of impacts, which is 0.29602 meter, and then for the standing pedaling 0.22207 meter, and the last one is seat pedaling at the 0.19047 meter. So the overall we can see for this project is that the mountain bike frame is extremely strong and safe, as indicated by a safety factor of 15 across all tested than a single rider would ever apply. Even during this means the frame can handle a force of up to 45,000 Newton, which is far more than a single rider will ever apply, even during very aggressive riding or large jumps. So last but not least, the test proved the frame is robust enough for real world mountain biking without any risk of breaking or failing. So thank you for me and for all my members group. That's all.